Okay, I'm going to wrap up one of the problems we started yesterday. A farmer has 1,600 feet of fencing and wants to fence off a rectangular field that borders a straight river. So you have a river here, and he wants some fencing, something like that. So you're going to have a width, and then a length. So that's one way to think about it. So we basically have two different things we're considering here. We're considering the perimeter, and then we're also considering the area here. So we know that the perimeter is going to be 1,600 feet is how much fencing we have. So 1,600 is equal to 2 widths but only 1 length because we're not fencing in that side along the river there. So the area is for a rectangular area, rectangle. So it's just going to be area is equal to length times width. So you can see we're dealing with length and width in both of these. So we basically have a system here that we want to solve. So I want to maximize the area. So this is the function I'm really interested in. So my function is going to be area based on, it could be length or width here, and I need the two different dimensions for that. Okay, so what I'm going to do is I'm going to solve for, let's say, L in this equation. So L is just going to be 1,600 minus 2W. So when I do length, I'm actually going to put in 1,600 minus 2W, and that will be times the width as well. So I have length and width. So this is a function for area based on width. So that's how we're going to write that out. So what we need to think about is what this would look like in terms of the graph. So I don't really actually have to multiply this out because it's given to me in factored form. And basically I would have a root or an x-intercept at 0. And then I'm also going to have 1, if I set that equal to 0 to solve, I would get 1 at 800. So when I think about that, I can see that I would have a negative Lie coefficient. So it's going to sort of do something like this. So what I need is to maximize that area. So I need this maximum location here. Okay? So I do know that if this is 0 and if this is 800, then I know this is located at 400 for the x, and I could literally just plug that in to get out the y. So, and that would maximize that area. So area based on 400 is going to be 1,600 minus 2 times 400, and all that is multiplied by 400. So I'm going to get, of course, that's just going to be, sorry about that, 1,600, just double checking everything, and I'm going to get 800 times 400, so it's going to give me a maximum area of 320,000, and this is given in feet, so it would be feet squared. Okay, now I want to show you how you would find that in your calculator, but what we are asked for in this specific problem were the dimensions. So the dimensions are going to be 400 for the width, and if the width is 400, then the length would be 800. So this is really what the problem asked for. I found a certain location, 400, and then it's going to be 320,000 right there. Okay, so on the graphing calculator, I'll just kind of show you what that would look like. So I already have it in here. So let me set my window. I need to make this go a little bit bigger. So I need to go, let's say 330,000 should work. Okay, so there we go. We'll graph that and see what it looks like. So there we can see our maximum value, but let's locate it because sometimes we won't be able to find it because of the symmetry And if it doesn't cross at x equals 0, then it's hard to find the symmetry sometimes. It's hard to find the vertex. So I'm going to do second, calculate. I'm going to go to max, which is 4. And I know I'm just going to kind of go to the left of the maximum point, press enter, and then travel to the right of the maximum point. Continue on, press enter, and then guess. So it's giving us 400, that's rounding to 400, and then 320,000, just like we found. All right, so, but our answer is we would have a width of 400 and a length of 800. Okay, let's do another one. So a company needs you to design a box with no top from a square piece of cardboard. The company wants the height of the box to be 3 inches and the volume to be 432 inches cubed. So let's write a formula. Before we do that, let's just kind of do a little sketch here of what we're talking about. We have a square, and we're actually going to fold up the corners to form a little box. So it's going to be like a box that has no top. But what I'm going to do, these are kind of where we would fold. So this area right here is going to be the base of the box, and then these squares in the corners would just sort of, we would cut those out and we wouldn't use those. We'd fold up these 4 flaps. So these 4 flaps would get folded up. You'd have to tape them and it'd form a box. So that's what we have going on here. But it tells us that we're starting with a square and that the height of the box is to be 3 inches. So really what they're telling us with that is that 3 is this dimension from here to here, because when it folds up, that's going to be the height. So the height is 3. And it's telling us the volume is going to be 432 inches cubed. So to write a formula for this volume, remember volume is going to be length times width times height. And we do not know any other dimension but 3. But we do know that they're all the same, like from here to here is x, if we want to call it that. And then I'm just kind of flipping my paper here. And then from here to here is also x. Okay, so what we can do with that is we can say that the volume of the box, and we need the area of this base right here, times the height of 3. So I don't know the length and the width here, but I know I could say that this piece right here is x minus 6, because if I have my unknown dimension for the square piece of cardboard. So I'm going to say I have x minus 6. And I'm going to say volume based on x, and x would be the original dimensions of the square piece of cardboard. And then I'm going to have, for the other piece here, it's the same thing. It's x minus 6, but all of that would get multiplied by 3. So I'm going to put a 3, I'll stick it out front. Okay, so that's the function that we could use, and it would give us the volume depending on the size of the original square box. But we want the volume to be 432 inches cubed. So I'm going to go ahead and set that in place, put that in place for volume, and I'm going to, I could go ahead and distribute this, so it's going to be x squared minus 12x plus 36. Okay, so there's my function. And I want to basically graph this because I'm trying to find out what I need x to be. So I'm going to graph this. Now, to do that in the calculator, I want to subtract 432 over. So I'm going to want to subtract that over. Actually, I don't even have to graph this. I could just go ahead and solve it from right here. From right here, instead of distributing this out, if I had just left it 432 is equal to 3, and then I have x minus 6 all squared. So I'm just going to start by dividing both sides by 3. So then I get 144 is equal to x minus 6 all squared. Then I would square root both sides. Plus and minus 12 is equal to x minus 6. So then I get x is equal to 6. So I'm just going to add that over. And then I'd have 6 plus and minus 12. So I'm going to get x is equal to 18. Now if I did x minus 6, I get negative 6, and that's not going to work for a length there. So x is equal to 18 is going to be the original dimension of the box. Okay? So this is the answer to this right here. X is equal to 18, and it's going to be inches. All right, let's do another one. An open box is made from a rectangular piece of material 15 centimeters by 9 centimeters, so it's a rectangle, by cutting equal squares from the corners and turning at the sides. So same kind of scenario here, except now I'm not dealing with a square base. Okay, I'm not dealing with a square base. So I know the dimensions 9, or I could say 15 there. I'll probably say 15 here and 9 here. So from there to there is 9, and from here to here is 15. All right, so I'm again making a box without a lid, and this would be the base of that box, and then when I fold up the flaps, I'd get the height of the box for the volume. Okay, so it does tell us the squares are equal, so that means this is x, so that's going to help us out there. So find the dimensions of the box that will yield a maximum volume. So let's go ahead and write out the function. So volume, based on the size of x, basically the size of the square you're cutting out, will be based on this length here, which is going to be 15 minus 2x, because I'm going the distance of 15 across. Sorry, the distance of 15 across, but I have to take out this x and this little x to get this 15 minus 2x. And then, of course, this is just going to be 9 minus 2x as well, because that's an x and that's an x. So 9 minus 2x. And then, of course, when I fold the flap up, the height will be an x as well. So that is the function that we're dealing with. And we want to maximize that function. So what we're going to do is we're going to put this in our graphing calculator, and we're going to find the maximum location for this. So go ahead and in your graphing calculator, go ahead and enter the function. Now you notice we haven't set it equal to any specific volume. We're trying to maximize the volume, so we're going to do that by finding the maximum location. And, sorry, 15 minus 2x, and then 9 minus 2x as well. Okay, now I'm going to go back and set my window to something a little bit more reasonable. Let me just do negative 15, 15. We had to change it so much for the other one because it had such a large area for that perimeter with the perimeter of 1600. So here we go. Let's just see what it looks like. I may not be able to see all of it yet. And I cannot. So my y's are not large enough because my y's are my volume because the function is for volume. So I need to change the window a little bit. I'll just do negative 100 to 100, and I kind of like symmetry. So there we go. Maybe we can see the whole thing now. Okay, almost we can. What we want is this maximum location up here. Now, this is saying volume is negative. So you know how we talked some about where is your polynomial above or below the x-axis. None of these x's in here will work for us, okay? However, these x's over here may work for us. So what I need to do is first I'm going to just find this maximum location, but I want y'all to start thinking about which x's are viable for this problem. So I'm going to do second, calculate, and I'm going to go to maximum. And I can see it's between 0 and, let's say, like 7. So I'm going to do 0, enter. It's just another way to say left bound. And let's just do 7, enter. You know what? I'm going to kind of go around. I don't want to be that far past that other one. Okay, enter, enter. So I have, somehow it went away. Let me do it again. So I'm going to do 0, and maybe this I'll do 5 for the right bound. And that should work. You just want to make sure your maximum location is actually between the two cursors here. So press enter, and it's going to be 1.82. And that's going to give us a volume of, that would be the maximum volume right there. Okay? So again, we just did something a little bit different there. So I am going to have hold on just a second, 1.82, and I need the dimensions here, so it's going to be 1.82, and then all I'm doing is basically saying that's my x, so that's going to be this height right here, okay? And then I need to do 15 minus 2 times 1.82, and that's going to give me 11.36. And then I also have 9 minus 2 times x, and that's going to give me 5.36. So those are my dimensions in centimeters. Now it says find the values of x such as the volume is specifically 56 centimeters cubed. So I'm going to go back and I'm going to replace the v of x with 56. So it's going to be x and then 15 minus 2x times 9 minus 2x as well. And what I'm going to do is I'm going to basically think about how I could solve this. Okay, I'm going to subtract 56 over, and if I'm going to go put it in the calculator, I'm not going to worry about multiplying this out. I'm just going to say in my function y sub 1 is equal to x 15 minus 2x times 9 minus 2x minus 56. And this is what I'm going to put into my calculator. And I'm going to solve it when I do that. So I have, all I'm really going to do is subtract the 56 at the end, because I already have all this in here. So subtract 56 and graph it. Basically, the whole graph is just going to shift down 56. I'm no longer interested in the max or the mins. I'm looking for these points of intersection. Okay, so I'm going to basically figure out where this is valid. So I need to find that location. So I'm going to do second, calculate, and now I'm going to find 0, the 0. So I'm going to go here. I'm going to travel along. And as long as I'm to the left of it, I can press enter, go to the right of it, press enter, and press enter again. So 3.5 is one of my roots, okay? And if you thought about it, that's a possible rational root. It would be in our list. So it would be 7/2. Then I also need to find the other location. Now, these values from here to here, will they work? They will not. I want to find this location, this value over here. So second, calculate, again, 0, and I want to go to the left of the x-intercept, press enter, and then go to the right, press enter, and then I get 8. Okay, so far I found 3.5 and I found 8, and I'm not quite sure what's going on over here, except for the fact that when I think about my function, that is going to give me, no I don't, because it's not in standard form, so I have to go and look at the data table and see what's happening. So do I have a root at 0 is what I'm trying to figure out. And I do not, but it happens between 0 and 1, so I need to go find that root. So second, calculate, option 2, and I'm just going to say 0 is a left bound, enter, and I'm going to say like 2 is a right bound. Okay, and guess, and then I get 0.5, so 1/2. So I have found 3 locations that work for this. Okay, I got an x of 1/2. I got an x of 7/2, or 3.5. And then I also got an x of 8. Now, we haven't talked about this yet, but I need to make sure that all of these values will work. Basically, I can't have negative dimensions, but I also have to make sure that each of these is at least 0. Okay, so all 3 of these will work in this first function, but if I look at this one, if I plug in the 8, 15 minus 2 times 8 is 15 minus 16. 8 will not work, okay? And definitely it won't work in this one. But the 3.5 will work here, and it will also work here, because 3.5 times 2 is 7. So 15 minus 7 is positive, 9 minus 7 is positive. So your two possible x values that could give you a volume of 56 cubic centimeters would be 0.5 and 3.5, and those would be in centimeters. All right, so that wraps it up, and we're going to pick up tomorrow with kind of combining inequalities with these word problems. So tomorrow be sure to be here, and we will do that.